This presentation covers the history of hydrologic changes in the Everglades, current conditions, and their ramifications for ecosystem restoration. Water is the lifeblood of the Everglades and the South Florida economy. The Everglades watershed begins in the headwaters of the Kissimmee River and flows southward 70 miles into Lake Okeechobee. Historically, a shallow sheet of fresh water flowed for 100 miles from the southern edge of Lake Okeechobee to Florida Bay. The water moved slowly over the extremely flat Everglades landscape through the wetlands into coastal bays and estuaries, creating a river of grass. Today, this diverse mosaic of landscapes and seascapes supports a complex natural and man-made ecosystem linked by flowing water. Human development altered the South Florida landscape. Drainage projects in the greater Everglades watershed began in the Kissimmee River Basin and the upper Caloosahatchee wetlands in the 1880s. By the 1920s, 6 major canals redirected water from Lake Okeechobee to the Atlantic and Gulf coasts. During the 1930s, a levee system was constructed around much of Lake Okeechobee, and by the 1950s, the northern Everglades were diked and drained to form the Everglades agricultural area. By the 1960s, the central Everglades were enclosed with levees forming 5 water conservation areas. The overall goal of this project was reclaiming the swamp to promote agricultural and urban development. By the early 20th century, this combination of land use and water management actions disrupted the Everglades' natural water flow and ecosystem functioning. By the 1980s, the adverse impacts of drainage and development in South Florida were well recognized. The state of Florida and the federal government began major land acquisition programs and several localized restoration projects in the Kissimmee River and southern Everglades. In 1996, Congress directed the U.S. Army Corps of Engineers to conduct a reevaluation of the Central and Southern Florida project for flood control and other purposes. In 1999, the Corps completed the CNSF restudy, Final Integrated Feasibility Study and EIS, laying out a plan to reverse the major unintended impacts to the South Florida ecosystem attributed to the Central and Southern Florida project. The restoration actions were designed to address landscape scale alterations from widely fluctuating water levels in Lake Okeechobee and excessive flows to the northern estuaries to detrimental water depths and hydroperiods in the Everglades and insufficient flows to the southern estuaries and degraded water quality. This listing of adverse water management changes in South Florida will be used as our outline to compare the pre-drainage and current conditions and describe restoration guidelines. Lake Okeechobee receives runoff from an upstream watershed covering over 4,000 square miles. The pre-drainage average annual inflows based on the Natural System Regional Simulation Model were approximately 2.2 million acre-feet, which included flows from adjacent marshes upstream of the Caloosahatchee and St. Lucie estuaries. Average annual outflows from the lake were approximately 1.8 million acre-feet and predominantly southward to the Everglades. Pre-drainage lake levels were estimated to fluctuate between 19 and 22 feet NGVD based on rainfall conditions in the watershed. The boundary of the lake varied seasonally as the adjacent wetlands were flooded and receded. Lake Okeechobee still receives the runoff from the upstream watershed covering the same 4,000 square miles, but the lake is cut off from the adjacent pre-drainage marshes by the Herbert Hoover Dike. Current average annual Lake Okeechobee inflows, based on the regional simulation model, are approximately 1.9 million acre-feet, and the reduction is likely a reflection of the redirection of flows from the Caloosahatchee and St. Lucie marshes. Average annual outflows from lake are approximately 1.4 million acre-feet per year, with regulatory releases made predominantly to the northern estuaries and with minimal flows to the Everglades. Current Lake Okeechobee water levels fluctuate between 10 and 17 feet NGVD based on rainfall conditions and water demands in the watershed. The boundary of the lake is now fixed, so prolonged high lake stages cause adverse impacts to the lake's littoral zone. Changes in inflows to the Central Everglades or water conservation areas, the red line on this graphic, reflect the impacts of upstream rainfall, diversions to tide, and water management operations in the Everglades agricultural area. Under pre-drainage conditions, average annual inflows to the Central Everglades rose more gradually, reaching a clear peak at the end of the wet season in October, then gradually receded throughout the dry season until the beginning of May. Under current conditions, average annual inflows to the Central Everglades tend to rise more rapidly than the pre-drainage estimate, reaching a more distributed wet season peak and then recede much more quickly through the early dry season. This leaves limited availability of dry season inflows before the start of the next wet season. Note that both the average annual flow patterns predicted by the Central Everglades project and the full SERP simulations follow the same basic wet season pattern as current conditions, but show strong improvements in the dry season flows that extend recessions. Surface water timing in the Southern Everglades, blue line on this figure, tends to maintain more consistent pattern for both the average annual pre-drainage and current conditions. This is likely due to the overland flow processes that tend to smooth out flows timing. Both the pre-drainage and current average annual flow patterns in the Southern Everglades gradually rise to a peak in October and recede more uniformly through the dry season. The Central Everglades and full SERP simulations tend to diverge more in this location since the average flow volumes are much larger under the full SERP due to the additional infrastructure that delivers flow from an eastern flow path which captures seepage and returns flows south of Tamiami Trail. The average annual pre-drainage flow volumes into the Central Everglades, the red line, are estimated to be approximately 800,000 acre-feet higher than the current average annual flows, with most of this difference reflected in lower dry season flows. Note that this annual flow volume difference is comparable to the average wet season regulatory releases from Lake Okeechobee to the northern estuaries. In other words, the reduced flows are largely the result of diversions to tide. Average annual pre-drainage and current flow volumes into the Southern Everglades, the blue line, show a similar reduction of approximately 1.2 million acre-feet, with shortfalls in both the wet and dry seasons. The average annual spatial pattern of overland flow reflects the greatly reduced spatial scale of the wetlands from the pre-drainage to the current conditions. The flow vectors similarly show the substantial reduction in flow rates that reflect the reduced flow into and throughout the Everglades. This figure compares the higher estimated pre-drainage ground elevations resulting from thousands of years of peat accretion with the current ground surface elevations that reflect a loss of peat soils due to lowered water levels and hydroperiods, as well as adjacent development impacts. Note that the major changes occur in the areas where there's been peat loss inside the Everglades agricultural area, on the western side of Dade and Broward counties, and along the Marl Prairies south of Tamiami Trail. This figure compares the pre-drainage and current water depth estimates along a longitudinal profile down the center of the Everglades. The pre-drainage NSRSM water level profile remains parallel to the ground surface, and water levels remain above the ground surface, supporting peat accretion. By contrast, the current condition with reduced surface water flows into the Everglades results in lower water depths that drop below the ground surface, resulting in peat subsidence in areas where water levels are substantially lower. The compartmentalization of the Central Everglades also causes ponding upstream of levees and drying downstream of levees, contributing to the loss of tree islands. The predicted pre-drainage average October water depths were more uniform and consistent across the gently sloping central Everglades and extended eastward to the Atlantic coastal ridge, and also show a minimal stage reduction along the lower Mall prairies adjacent to Shark River Slough. By contrast, the current average October water depths show altered patterns across the Everglades, reflecting the locations of canals and levees, and show the loss of former wetlands along the backside of the Atlantic coastal ridge. The predicted pre-drainage average April water depths again remained uniform and consistent across the gently sloping Everglades, but showed water depth reductions along the lower Marl prairies adjacent to Shark River Slough. By contrast, the current average April water depths showed altered water depth patterns across the Everglades, with deep dry downs along the Atlantic coastal ridge. April water depths also show irregular ponding in the Everglades upstream of levees and extensive drying in the northern portions of each of the water conservation area impoundments. Finally, the Marl prairies adjacent to Shark River Slough go completely dry, contributing to peat loss and subsidence. The Biscayne Aquifer underlying the southeastern portion of the Everglades has some of the highest transmissivity rates in the U.S. Seepage losses are particularly high along the L30 and L31 canals and levees adjacent to water conservation areas 3A and 3B and Everglades National Park. Additional seepage management will be needed as we implement later SERP projects to maintain Everglades restoration benefits and reduce flooding risks in adjacent developed areas. Paleo-environmental studies by the U.S. Geological Survey have been used to set freshwater flow restoration targets for the southern estuaries. These targets have been adjusted to reflect sea level rise scenarios. Adjusted salinity targets at key sites in Florida Bay can be used to evaluate restoration performance. The results indicate improved performance from the Central Everglades project, but additional dry season flows will still be needed. Water management operations, November 2024 to March 2025. The graphic shows water level hydrographs for Lake Okeechobee, top graph, and Water Conservation Area 3A, bottom graph. The text describing changes in water management operations as we transition from the 2024 wet season to the 2025 dry season. In the middle of November 2024, point A on the graphs, water levels in Lake Okeechobee were at their annual peak at just over 16 feet. Lake Okeechobee levels were near the historic upper peak, 10th percentile, but it changed little in the last 30 days, remaining within Zone D, or normal operational range, for the Lake Okeechobee System Operating Manual, or LOSOM, schedule. Water management operations were forecasting a weak La Nina dry season, and lowering the lake into the recovery zone was contemplated. Lake Okeechobee inflows and outflows were nearly balanced, while outflows to the south were limited by high water conditions, with all three of the water conservation areas in Zone A or their upper regulatory zones. At this time, Water Conservation Area 3A had just dropped below its historic 10th percentile, and outflows were at their maximum allowable levels. By the early dry season in January 25, point B on the graphs, Lake Okeechobee stages were near the upper 25th percentile and dropping steadily. Lake Okeechobee outflows were increased to try to reach the ecological recovery envelope to promote recovery of the littoral zone emergent and submergent aquatic vegetation. Flows southward into the stormwater treatment areas are limited in the dry season to less than 750 CFS to allow recovery of their vegetation communities. Water Conservation Area 3A water levels had dropped into Zone B, and outflows to Everglades National Park followed the Tamiami Trail flow formula. By the mid-dry season in March 2025, point C on the graphs, Lake Okeechobee stages were well below the historic 50th percentile and receding fast. And we were well inside the ecological recovery envelope to support the lake's littoral zone. The stormwater treatment area recovery constraints continue to limit inflows to the water conservation areas. Flows into and through Water Conservation Area 3A were dropping quickly, but we continued to follow the Tamiami Trail flow formula of water deliveries to Everglades National Park. Changes in water depths in Lake Okeechobee and the Everglades. This graph shows the changing water depths in Lake Okeechobee and the downstream Everglades as we transitioned from the 2024 wet season to the 2025 dry season. In mid-2024, the left maps, water depths in Lake Okeechobee were at their annual peak, and the littoral zone was fully inundated. Most of the downstream Everglades were inundated, except for the marl prairies in the Big Cypress and the Rocky Glades. Water depths were highest in the central Water Conservation Area 3A region, where damaging high water levels routinely form behind the downstream levees. By January 2025, center maps, Lake Okeechobee littoral zone was beginning to dry down, and high water conditions in the water conservation areas were receding, but surface water flow connections were still intact. By March 2025, the right maps, nearly all of Lake Okeechobee littoral zone had dried down. Water levels in the marl prairies had dropped well below the ground surface, and the northern or upstream portions of the water conservation areas were drying down rapidly. At this point, the surface water flow connectivity between the central and southern Everglades was beginning to be lost, particularly in the eastern portions of Everglades National Park and Taylor Slough. Comparison of inflows to water conservation areas versus inflows to Shark River Slough, 2005 to 2024. This graphic compares two periods of base period from 2005 through 2017 versus the more recent period from 2018 through 2024. These time periods match the baseline and reporting periods for the 2024 Recover System Status Report. This latter period also matches the U.S. Army Corps of Engineers' initiation of field tests of increased flows into Northeast Shark River Slough, leading to the implementation of the combined operational plan. For the inflows to the water conservation areas, the 2005 to 2017 base period and the 2018 to 2024 reporting period, the upper graph, have similar patterns, but with higher flows in May and June at the start of the wet season for the 2018 to 2024 period. Overall, the 2018 to 2024 period shows higher flows for the transitional months at the beginning and end of the wet season, likely reflecting rainfall differences. For the inflows to Shark River Slough, the lower graph, the latter period, 2018 to 2024 reporting period, shows substantially higher flows throughout the year, with a smoother transition between the wet season and the dry season. This later Shark River Slough inflow reporting period reflects several operational changes, including the lowering of the Water Conservation Area 3A regulation schedule line in 2016, raising the L29 canal stage constraint in 2017, and a higher demand to move water south into Shark River Slough based on the Tamiami Trail flow formula implementation in 2020. If we compare Shark River inflows to the Water Conservation Area inflows, they've increased from roughly 50% of the time in the base period to 88% of the time in the reporting period. Improving water quality conditions in the Everglades, stormwater treatment area performance. This graphic shows the stormwater treatment areas and how they have lowered nutrient levels for inflows entering the Everglades protection area. The right graph shows the period of record time series graphic. Over the last 30 years, the combined stormwater treatment areas have treated approximately 27.8 million acre-feet of water and retained over 35,000 tons of total phosphorus, or 78% of the cumulative total phosphorus load. The sharp increase in inflow total phosphorus loads beginning in 2002, bottom graph, reflects the startup of construction period as we increased the treatment capacity of the stormwater treatment areas. The graphic showing the individual performance of the stormwater treatment areas, bottom left, shows that Stormwater Treatment Area 2 and Stormwater Treatment Area 3-4 in the Central Everglades Agricultural Area flow path received the largest inflow water volumes and produced the lowest flow-weighted mean outflow total phosphorus concentrations. This is likely attributed to their larger combined treatment footprint and the benefits of controlling the hydraulic loading rates via the adjacent A1 flow equalization basin. This central flow path has been achieving the state-required water quality-based effluent limit, or QBEL, for several years, while the eastern, STA 1 East-West, and western, STA 5-6 flow paths have not reached this level of performance. Changes in TP concentrations in the downstream Everglades. The Florida Department of Environmental Protection has interpreted the narrative water quality treatment requirement of no imbalances in native flora and fauna to establish a long-term geometric mean of 10 micrograms per liter total phosphorus in the Everglades. The map on the left shows the water year 2024 annual total phosphorus geometric mean concentrations for monitoring sites throughout the Everglades. Except for sites adjacent to direct canal outflows, the marsh sites show concentrations of less than 10 micrograms per liter throughout the Everglades. The graphic on the right shows the temporal changes in the annual mean total phosphorus from 1979 to 2024 for both inflow and interior sites in the Loxahatchee National Wildlife Refuge, Water Conservation Area 2, Water Conservation Area 3, and Everglades National Park. During the inflow baseline period, 1979 to 1993, before the stormwater treatment areas were constructed, total phosphorus concentrations at both the inflow and interior sites reached historic highs and were highly variable. During inflow period 1, 1994 to 2004, total phosphorus concentrations were reduced as the STAs came online. During inflow period 2, 2005 to 2023, total phosphorus concentrations generally continued to fall, but experienced extreme climatic conditions related to hurricanes, intensive rainfall, and periods of extended drought that impacted total phosphorus concentrations. The ENP transect shows the greatest response to these period 2 climatic events, as well as recent operational changes that deliver higher flows at lower upstream marsh elevations when total phosphorus concentrations tend to increase. Modeled surface water flow vectors under the combined operational plan and full Central Everglades Planning Project implementation. This graphic shows the modeled surface water flow vectors within Water Conservation Area 3A and 3B and Northern Everglades National Park under current conditions of the combined operational plan on the left, which was implemented in 2020, compared to full implementation of the Central Everglades Planning Project on the right, anticipated by the mid-2030s. Under current conditions, the combined operational plan, the highest surface water flow vectors run from the S11 inflow structures on the northeast side of Water Conservation Area 3A and follow the L67A levee southward to the downstream S333 structures, then entering northeast Shark River Slough. Additional flows from the north at the S8 pump station pass down the Miami Canal, then spread out into the marsh at plugs in the canal. A second set of high surface water flow vectors enter the marsh along the west side of Water Conservation Area 3A from the Big Cypress Basin via Mullet Slough and run along the L28 levee then pass through the S12 structures into western Shark River Slough. After full SERP implementation, the highest surface water flow vectors enter Water Conservation Area 3A from the northwest. The Miami Canal is partially backfilled, spreading surface water flow vectors across the marsh. The new Blue Shanty flowway introduces surface water flows into the southwest corner of Water Conservation Area 3B. Internal canals are partially backfilled, and a portion of the L29 levee is removed, which creates a direct flow connection with northeast Shark River Slough. Flows entering Water Conservation Area 3A from the west would spread more uniformly into Water Conservation Area 3A marshes, then pass southward into Everglades National Park.